Today we're going to dive into what I think is one of the most elegant programming tricks ever come up with. We're talking about an idea from the absolute legend, computer scientist Donald Knuth, that uses a beautifully simple concept to solve these mind-bendingly complex problems. Everything from Sudoku to insane scheduling puzzles. So let's start by looking at a puzzle that seems almost impossible to crack. Okay, let's kick things off with a puzzle that, on the surface, seems almost impossible for a computer to solve efficiently. I want you to imagine trying to find one specific path through a massive, tangled forest where pretty much every single turn you take leads to a dead end. So take a look at this. This chaotic web you're seeing is a search tree. It's basically a map of a computer's attempt to find just one single solution to a tiling puzzle. The goal is to fit 12 totally unique shapes, they're called pentominos, onto a chessboard. Every single branch you see here is a choice the computer makes, and as you can probably tell, most of them go absolutely nowhere. Figuring out how to navigate this maze without getting lost forever, well, that's the core of our problem.
And believe it or not, this is not a new problem. Way back in 1958, a graduate student named Dana Scott programmed the MANIAC computer to take on this exact puzzle. It took a whopping 3.5 hours, which was a gigantic amount of computing time back then, just to find all 65 solutions. It really goes to show you how long we've been obsessed with these kinds of challenges.
But, okay, here's where it gets really interesting. That pentomino puzzle, and a whole bunch of others, like Sudoku, they're all just different disguises for the exact same deep underlying problem. And once you understand that core structure, you can solve all of them with the same elegant tool.
And that underlying problem? It's called the exact cover problem. Now, I know it sounds a little academic, but the idea is actually super simple. You've got a grid of zeros and ones. Your goal is to pick out a specific set of rows so that for every single column in the grid, you have exactly one 1 among the rows you've chosen. That's it. This is the skeleton key to everything.
All right, let's make this real. Here's a small example right from Knuth's paper. We need to cover all the columns, A through G, so you might start by trying out a row. What if we pick, say, row 2? Cool, that covers columns A and D. But now we have to cover all the rest, so maybe we try row 6. That gets us columns C and E. Okay, now we have to cover B, F, and G. If we can find that perfect combination of rows where every single column is covered exactly one time, we've solved it. The idea is simple, right? But actually finding that perfect combination is incredibly hard. So how in the world do you find that solution? Well, the most obvious way is just a brute force approach. You make a choice, you see where it goes, and if you hit a dead end, you have to go back and try something else. This whole process is called backtracking. The logic itself is pretty straightforward. You pick a column you need to satisfy, then you try a row that has a 1 in it. Then you temporarily remove everything that clashes with that choice, and you try to solve the new smaller puzzle. But the key and the real problem is step 5, backtracking. If you hit a dead end, you have to undo everything you just did, perfectly. And this right here is the absolute heart of the problem. Undoing your moves is expensive. A simple program might just save a complete copy of the puzzle every time it makes a choice. But for a complex problem, that's like photocopying an entire phone book every single time you look up one number. It's just ridiculously slow and eats up all your memory. Okay, so this brings us to the beautiful core of Knuth's paper. He found this unbelievably elegant way to solve this whole undo problem without making any copies at all. He asked this one central question. Just imagine you have an item in a list. How can you remove it and then later on put it back exactly where it was, using only the information that's already inside the item itself? No backups? And here is the answer. It's so simple, it's brilliant. In what's called a doubly linked list, every item has a pointer to what's before it and what's after it. To remove an item, you just tell its neighbors, hey, point to each other now and just skip me. But here's the magic. Look at the second operation. The item you removed still remembers who its old neighbors were. So to put it back, you just tell them, hey, point back to me. The restore operation is a perfect mathematical inverse of the remove operation. No backup needed at all. You know, even Knuth himself had that aha moment. He said he felt a definite sense of discovery when he figured this out, because it seems like after you remove the item, its internal pointers should be useless. But they're not. They hold the secret to its own revival. So let's see how this one simple trick becomes the engine for this incredibly powerful algorithm, an algorithm that Knuth gave the perfect name, dancing links, because the pointers really do perform this exquisitely choreographed dance to solve the problem. The crucial idea here is that instead of making copies, the data structure itself fluidly changes shape.
When the algorithm makes a choice, a bunch of pointers get rewired to temporarily hide all the conflicting options. Then, when it needs to backtrack, the pointers simply dance back to their original positions, perfectly restoring the puzzle to how it was before. So here's the forward step of the dance: covering a column. First, you take the column header itself out of the list of active columns. Then, for every single row that has a 1 in that column, you go through it sideways, removing each of its other elements from their own column lists. It's like this cascade of temporary removals. And uncovering? Well, it's just the dance in reverse. You do the exact opposite operations in the exact opposite order. The beauty here is that it's perfectly symmetrical and incredibly fast. You just put everything back exactly where you found it. All right, so that's the theory. It's elegant, for sure, but what's the payoff? I mean, how does this clever little dance actually perform in the real world on those hard puzzles we started with?
Well, the results are pretty staggering, actually. This table shows that pentomino problem again. Without any extra smarts, the algorithm still has to explore over 100,000 possibilities. But add one simple rule: always pick the column with the fewest available ones, and boom, the number of nodes it has to explore drops by 90%. And Dancing Links is what makes keeping track of that information super, super fast.
And this brings us right back to where we started. Remember Dana Scott's 3.5-hour computer run in 1958? By the 60s, a better program got it down to 10 minutes. Knuth's Dancing Links algorithm, which he called DLX, solved an even harder version of the puzzle in under a minute on a computer from the late 90s. Just imagine what it does now. And this really reveals the algorithm's secret weapon: abstraction. It has no idea what a piece or a board cell is. It doesn't care. It only sees columns that need to be covered. This means it can intelligently switch between asking, where can I put this piece, and what piece can I put in this empty cell? It just attacks the problem from whatever angle is the tightest, the most constrained. You know, Knuth's Dancing Links really shows us that sometimes the most powerful solutions aren't the most complicated ones. They're simple, they're reversible, and they're just elegant. And it kind of makes you wonder, right? What other tangled, impossible problems out there in science or art or just in our daily lives are just waiting for their own ha-ha moment? That one simple, beautiful trick that's been hiding in plain sight all along.